Hello Chem 1. Today we're going to take a look at our final gas law equation, the ideal gas law. Let's get started. The ideal gas law is another equation that takes a look at pressure, volume, and temperature and allows us to calculate what happens if we change one of those variables. This equation is specific for what we call ideal gases. With a real gas, particles have volume, they have attractive forces, and they have inelastic collisions. This equation requires us to assume that these gases are ideal. This would mean that particles have no volume. We can assume this because those particles are so small within a gas that their size is negligible. We can also assume that there's no attractive or repulsive forces. In a gas, particles are so far apart that the attractive forces don't really play a role in how those particles behave. And we also assume that collisions are elastic, meaning that when particles collide, no energy is lost. If we assume those three things, we can develop an equation where pressure, volume, and temperature are compared to one another, as well as moles of the gas. Based on the assumptions we've made, there are certain conditions where ideal gases don't exist or that this gas law does not work. If particles within the gas are very polar, they're going to have some attractive force, and therefore the ideal gas law starts to break down. In the same way, if there's a gas molecule that is very large and has a larger mass, it will also cause the ideal gas law to break down. And finally, if particles get too close together, this would be if we are at extremely low temperatures near absolute zero, or if we're extremely high pressures. In both of those situations, you could be close to the gas becoming a liquid, and the ideal gas law calculations will not model what is happening in reality. The ideal gas law relates all four properties of influence: pressure, volume, temperature, and N, which is the number of moles of the gas, or amount of particles. In this equation, often referred to as piv nRT, because if you sound it out phonetically, that's what it looks like, there's an R constant. This R constant is experimentally determined, and it is 0.0821 liter atmospheres per mole Kelvin. This is the number we will be using every time to put in for R. What that means is your other measurements, pressure, volume, and temperature in moles, all have to be in these units. Volume has to be in liters. Pressure has to be in atmospheres. Obviously, N is moles, and then temperature has to be in Kelvin. If we want to use that constant, the other measurements need to line up. This is just another look at the equation of piv nRT and what each variable means. Remember, N is the number of moles of gas we're talking about. Let's do an equation. It says calculate the number of moles, so right away we know we're looking for N. If a gas occupies a volume of 3 liters, and it's in liters, so we're good, a pressure of 1.5 atmospheres, it's in atmospheres, so we're good, and a temperature of 300 Kelvin. So we're looking for piv nRT. P is 1.5, V is 3.0, and we don't know. R, we do know. It's 0.0821 always. It is the constant times 300. We divide both sides by 0.0821 and 300. It would cancel on the right, and we'd get an answer of 0.18 moles. Just like our earlier equations, identify the variables, plug them in, come up with an answer. Here's another problem. You can see here we're given moles, we're also given volume, but the pressure is in 1073 torr. We have to get torr to atmospheres. So the first equation we're going to do, we're going to put torr on the bottom and atmospheres on the top. 1 atmosphere equals 760 torr. So we're going to divide 1073 by 760, and that gives us 1.41 atmospheres. And now we can plug that into our piv nRT equation. Our pressure is 1.41, our volume is 1, our number of moles is 2.49, 0.0821 is our R value, and T we do not know. That is what we are looking for. There's our first step, determining the number of atmospheres. And there's the second step. Notice we got 7 Kelvin. We would then convert that to Celsius by subtracting 273 to give us our answer in Celsius. Here's another problem solving for volume. Very similar to what we've done already. Just put the variables in the right location, solve for V. Another thing we can do with the ideal gas law is use it to find the molar mass of a gas. The most important thing to remember here is that molar mass, the units on molar mass, is grams per mole. So typically in these problems, you'll be given grams. And so if you calculate moles, you can put grams over moles and figure out your molar mass. We can also use the density equation to figure out the molar mass. Let's go through a couple examples of these. The first one here wants us to determine the molar mass. And we have 6.10 grams of pure gaseous substance. But the first thing we're going to do is set up our Pivnert equation. This needs to be converted to Kelvin, which would be 325. Our pressure needs to be converted to atmospheres, which would be 1.01. And our volume needs to be converted to liters, which would be 0.69 liters. Now we're ready to set this problem up. Pivnert's going to look like this. We have our pressure times our volume equals N, our number of moles, times our constant R times 325. If we solve this, we get the number of moles of gas, which is 0.0261. So far, nothing has changed. But it wants us to know, so far this is just a normal Pivnert problem. But it asked us for the molar mass. Remember, molar mass is grams per mole. So if I have the number of grams, 610, and I put it over the number of moles, that's going to give me grams per mole and tell me the molar mass of this substance. So here we have 610 divided by 0.0261, and that gives us a molar mass of 234 grams per mole. In this next problem, they're asking us to use the density to find the molar mass. The first thing we're going to do is set up our Pivnert problem as normal. We have 1.01 atmospheres and 1 liter. After we convert torr to atmospheres, we get 1.01, and we convert the Celsius temperature to Kelvin, we get 3.03. The other thing that we're doing in this problem is we're taking the density, which is 1.25 grams per liter. In other words, per 1 liter. So we are using the volume of 1 because the density is telling us we have this many grams for every 1 liter. So we'd solve and get the number of moles. And then remember, our molar mass is grams, which is 1.25 over the number of moles, 0.0406. So this gas would be 30.8 grams per mole. When you're calculating the molar mass with this Pivnert problem, you really need to understand the units of molar mass and the units of density and how you can use those to get to where you're trying to go. The last thing we're going to talk about here is gas stoichiometry. This is pretty simple. Since Avogadro's principle states that equal volumes of gases have the same number of particles, we can use the coefficients in a stoich problem to determine the volumes of gases that we'll need to make them react evenly. So if you look here what's going on, it says how many liters of methane are needed to produce 26 liters of water. In old mole problems, we would have to go from liters of water to moles of methane gas to liters of methane gas. But we know since everything in this equation is in liters and all liters are the same number of moles for gases, that we can just go straight from liters to liters using the coefficients. So if I have 26 liters of H2O, I'd go from liters of H2O straight to liters of methane in a 2-to-1 ratio because those are the coefficients. And I could just divide by 2 and know that I'm going to need 13 liters of methane to produce 26 liters of H2O. Here's another one down here. It's going to combust 2.36 milliliters of butane. And I know I can go from milliliters of butane straight to milliliters of oxygen using the coefficients, meaning that I'm going to need 15.3 milliliters of methane. I can do this because the mole ratios within those problems are the same as volume ratios because every mole of gas takes up 22.4 liters. Spend some time with these Pivnert problems and let me know if you have any questions. Keep up the good work. We'll see you soon.